Hi there. In this video, we are going to talk about how to solve systems of equations. Now, a system of equations is a list of two equations, is what we'll look at in this section, each with two unknowns. So you'll see two equations that have an x and a y in them. And the solution is going to be the ordered pair, x and y, that make both equations true. And the first way we're going to look at solving a system of equations is through graphing. Now, if you remember, when we graph a line, it's the solutions, it's all the solutions to that equation. So when I have a system, the point where those two lines intersect will be the point that is a solution to both equations at the same time. So when you're graphing to solve a system of equations, you're looking at the point where they intersect. Okay, so to solve these, you graph each function and identify that point where the two intersect, and that will be your solution to the system. So let's look at an example with this. Here I have the two equations, y equals negative 6x minus 2 and y equals 2x plus 2. I'm going to start out by graphing each one of those equations. Okay, however you want to graph it, whether it's a table or using the slope and intercepts, you can graph the equations. And then I'm looking for that point where they intersect. And it looks like for this one, they intersect at negative 0.51. Now, you can always verify this using technology like I did here. I used Desmos to graph this and identify that point. You can also plug these points into the equations and make sure that they give you a true statement in each case. But that's really all there is to graphing to solve a system of equations. The big drawback here is we're not always going to get nice numbers that are easy to identify. And when you need an exact answer, this is not the best way to go about it. But it will give you an answer pretty quickly if you get nice integers or nice fractions even, as this case. But if I need to solve these to get exact values without having to guess at it at all, then we have two other methods that we can use to solve a system. The first one, let's talk about solutions a little bit more first. Sorry, I got ahead of myself. So there are three scenarios visually that we can see for a system of equations. The one we just saw, where we have two equations that intersect at one point to give me one solution. It is possible to end up with a system where I have two lines that are parallel to each other and never intersect, in which case there is no solution to that system. So that can happen. The other option is it can turn out that all the equations are basically equivalent to each other. And when you graph them, you get the same line twice. And that means that every point on the line is a solution to the system. So we say infinitely many solutions. That doesn't mean that everything is a solution, but there are an infinite number of them because this line goes on forever. So solutions to systems, if there is at least one solution, so one or infinitely many, then we call that a consistent system. If there's no solution, it's inconsistent. If all of the solutions are the same for both equations, so that we have infinitely many, then we say that it's dependent. And if it is not dependent, then it's independent. So looking at these three scenarios again, the first one is consistent because it has a solution, and it's independent because the solutions are not all the same for both equations. The middle one is inconsistent because there's no solution, but it is independent. And the last one is consistent because there's a solution, but dependent because all the solutions are the same. Okay, so two other methods to algebraically find the solution without having to try and figure it out from a graph. So the substitution method, which this is written out in your notes, but I want to go over quickly the strategy that we're going to use, is you're going to take one of the equations, and there's a lot of flexibility here. You can pick the one you want to use, and you're going to solve it for one of the variables. So get it to say y equals or x equals. And then we're going to do a substitution. If I find what y is equal to in terms of x, then I can replace y with that expression in the other equation. And by doing that substitution, I'm going to end up with an equation with just one variable that I can solve. And once I've solved for one variable, I can go back and plug it into either of the original equations to find the second variable. Remember, there's always two numbers you're looking for when solving a system of two equations with two unknowns. And then it's always a good idea to verify that your ordered pair is actually a solution to both equations at the end. So with this strategy in mind, let's take a look at how substitution looks in practice. So here I have 7x minus 3y equals 5, and y equals negative 1/2 x plus 4. Now it turns out that the second equation is already solved for one of my variables. It's solved for y right now because it says y equals. So I get to skip that first step, which is an advantage that makes me want to use substitution here. And I'm going to take that negative 1/2 x plus 4, and I'm going to substitute it in for y in the top equation. Since they're equal to each other, they're replaceable. You can switch from one to the other. So I'm going to take that top equation, and wherever there's a y, I replace it with negative 1/2 x plus 4. So I end up with 7x minus 3 times the quantity negative 1/2 plus x plus 4 equals 5. Now the advantage to this is I no longer have any y's in the equation, I only have x's, and I know how to solve an equation with one variable. So I'm going to simplify this by distributing the 3. Combine my like terms. I've got two x terms there, 7x plus 3/2 x. I can combine. That gives me 17/2 x minus 12 equals 5. And now I'm going to start isolating that x. So plus 12 to both sides gives me 17/2 x equals 17. And then divide by 17 over 2, which gives me x equals 2. So I lucked out. Even though I had to deal with some fractions there, I ended up with a nice whole number answer. And I have found my first part of the solution. I've found x, but I can't stop there because I also need to find y. So I'm going to take the x that I found, go back to the original two equations, and plug it into one of those to find y. You can do it with either one because it has to be a solution to both. I'm going to pick the second one simply because it's already solved for y, less work for me to do. So the x is replaced by 2. I get y equals negative 1/2 times 2 plus 4. And I just plug that in my calculator to simplify. Negative 1 plus 4 gives me 3. So I have my solution to 3. Remember, put them in order, x and then y, as a solution to the system. And there are a lot of steps involved here, so it doesn't hurt to plug those in and make sure that it works in both equations before you move on. And that way you know that you got the right answer. And that is how substitution works. The third method for solving a system of equations is the addition method. And this one is sometimes called the elimination method. It works a little differently, but it's going to have the same result as the last one. So with this, I write them each equation in standard form, which means the variables on one side, the constants are on the other side of the equation. And then I'm going to be adding these two equations together. Before I add them, I need to make sure that when I add them, one of the variables will cancel out. So if there's a 2x in one equation, I want a negative 2x in the other equation so that when I add them, I end up with no x's. So I can force this to happen, if it's not going to happen naturally, by multiplying one or both equations by some coefficient so that when I add them, they will cancel like that. Once I've done that to one or both equations, I add the equations together and I will end up with an equation with just one variable. So just like with the substitution method, I found a way to eliminate one variable so I can solve for the other. From there, you just take that one solution, plug it back into the original equation, and solve for the second value. So let's see how this works in practice. Here, both of my equations are already in standard form. The x's and y's are on the left, constants are on the right. If I look at these two equations, if I were just to add them the way they are, the x's would not cancel, the y's would not cancel. So I'm going to have to manipulate something here. There's a lot of flexibility, so your work might look different from somebody else's, even if you end up with this, you should end up with the same answer. All right, so I look at this and I think, well, gosh, if I just multiplied that negative 3x by 2, then I'd have a negative 6x that would cancel with the positive 6x. And that looks like the easiest way to do this, so that is what I'm going to do. I'm going to take the top equation, multiply everything by 2. Can't just do it to the one term. I have to do it both sides of the equation every term. So I get negative 6x plus 10y equals negative 2. And now this new equation I'm going to add to the second of the original equations. All right, so plus 6x minus 2y equals 10. Negative 6x plus 6x cancels out. I end up with 8y, because 10y minus 2y is 8y. And on the right side, negative 2 plus 10 gives me 8. So I eliminated one of the variables so I could solve for the other. And if I just divide by 8, I get y equals 1. The most work usually goes into finding that first solution. From there, it can go pretty quickly. I found my first value. I'm going to go back to one of the first equations I started with. Really, any equation that has x and y in it will work, though. I'm just going to pick one and then solve for x. So I'm going to pick the second equation, 6x minus 2y equals 10, and plug in 1 for y. So I end up with 6x minus 2 equals 10. Let's add the 2 to both sides of that equation. So 6x equals 12. And then divide by 6 to get my solution. So x equals 2. And that means if I write that as an ordered pair, the point 2, 1 is a solution to the system. Okay, so you might be asking yourself, when do I use which method? Well, a lot of times I'm going to tell you which method to use, so you don't have to guess. But graphing is usually best when your solution is an integer. That's hard to know until you actually graph it. But usually you'll be told when to graph it. Substitution is great when one equation is already solved for, like the example we did, example 2, or can be easily solved for. The other occasion where substitution is usually my preferred method is when I have decimals in my coefficients. I usually don't want to bother with addition method when I'm dealing with some decimals or ugly numbers. So substitution is nice, particularly that happens in like an applications problem where numbers aren't as pretty. So substitution is the nicer one. Addition is great when they're in standard form, or if there's some fractions in there that you can wipe out by multiplying by a least common denominator. That's also a nice time to use addition. Addition tends to be the favored one. We're going to use it a lot more in the next section.